Thank you. Last session before the keynote, so thanks for everyone for remaining in here, and thanks for attending the session. As mentioned, I worked at Avery Technologies, did some algorithms there, did some of the elastic audio algorithms in Pro Tools 7.4, helped develop some of the AX hosting code in HDX, ended up writing the first AX DSP plugin. If you ever get a trivia question on it, it's Reverb 1, but no one knows that except internally. Dolby Laboratories, leading a development for content creation tools for our Atmos system. So my kind of transition has been like assembly to C++ to Python, back to C++. And I think that kind of arc has, over the years, taught me a lot about test-driven development and testing and why oftentimes in audio, it doesn't get focused on as much, and I think we can change that. I'm also a musician, a violinist, and unfortunately, I'm an electronic music producer as well. That's me and a bit more makeup in my project. So quick survey, no show of hands, but just think among yourselves, how many people use nightly continuous integration systems? Hopefully some of you. How many people use unit testing frameworks? Hopefully quite a few of you. And how many people use test-driven development practices already? Glad to see some hands. I'm sure some of you might even use TDD style if you don't even know it. How many people know that they should be testing more? And I hope everybody's hands internally go up. And if anybody here is opposed to these concepts, then thank you for coming. I know certainly in the audio industry there's a lot of people who are opposed to this style of thinking for various reasons. Let's talk about where we all started from, the dark ages. We have this thing called legacy code. And legacy code, we've all been there, we've all gotten it, we've all written some. It starts out, it's not tested because we're just excited to hack on things. So once we've written something and we need to add features, we're kind of hesitant to change things because it just works. But maybe there's someone in the company, maybe it's you, maybe it's someone else who can actually change this. But for everyone else, this is voodoo code. This is code that simply works and we don't exactly know why, whether it's because it's too complicated or the engineer is a junior, and it becomes hard to maintain. It becomes brittle. It becomes only understood by one person. If you ever are working in a company where you're going to this one person, they might be very smart, very intelligent, very good programmer, but it really, I think, becomes a problem with this code. You end up giving projects to your junior developers, or maybe even yourself. You just kind of code. You give it testers, you hope it's going to work, and inevitably this cycle starts to slow down development. So you think about this, you think, okay, we're going to start testing our code more. We're going to hire some QA engineers. Maybe we're going to do our testing ourselves. We're going to do some manual testing. So we're going to, after every build, we're going to do some sanity tests. So we're going to say, does this thing actually run? Does it not crash? Let's load it up in the DAW. Let's listen to it. Let's actually take some audio, run it through our plugin, and say, oh, okay, here's a distortion plugin. It's actually sounding distorted, or it's actually filtering the audio. I think it's kind of working. Maybe we're going to move some sliders. Yeah, it seems to change things. The EQ seems to go down and up. Let's call it good. Give it to a tester. Let them hack on it for a while. Maybe it's good, maybe it's not. But this cycle is really, really slow. At best, if you're doing the development yourself, you've got 10 minutes between when you make a change and when you can actually hear that things are working. So maybe you're thinking, okay, we've got to get faster than this. We've got to become more modern. I've heard about this thing that's like test-driven development. Let's try this. But before that, as an audio engineers, we think, okay, we can take this cycle, this 10-minute cycle, and we can make it automated. We can give it to a CI machine. Okay? It's better than nothing. Cancellation tests are great. I use them all the time, especially when we have a known good response. Maybe it's from a research team. Maybe it's because you have an algorithm that works. You're just going to want to optimize this code. You want to make sure it's exactly the same as what you had before you started optimizing. So you load up some cancellation tests. Unfortunately, this doesn't cover everything, and it has lots of problems, such as, if you're going to change your algorithm with something minor, let's say your filter implementation changes slightly, well, all of your responses in your cancellation tests are going to change. And so you're just going to have to regenerate those tests, regenerate the input response and the output response, and hope that, well, this new normal is in fact tested. And I've found in my experience, this ends up just being throw a bunch of content at it. At Dolby, one of the things we do is we say, of course, we make codecs. And so we make codecs for movies. And the movies end up being 2 hours in length. And it starts out, yeah, you've got little snippets of audio that you end up testing, but then we'll just run it through like hours and hours and hours of audio with no real rhyme or reason other than it needs to match the input response that we had before any changes were made. So let's say, okay, we're gonna do this automated build test cycle, and I'm not gonna go into this too much, but CI practices, after every night, every change, we're going to check it in. We're gonna have it automatically compiled, built, run, tested automatically so that no testers have to be in the process. Of course, testers fear for their jobs. They say, oh, we're gonna be replaced. That's not necessarily the case. And so this build test cycle becomes quicker, becomes more deterministic, becomes more visible, because everyone can see when it succeeds or fails, but it's still driven on this cancellation idea. So of course, you know where I'm going with this. We're saying, let's have the developers do this testing. Let's have it not be comparison-based, but let's have it be very self-contained. I've been reading a lot about unit testing, and a lot of people talk about this first principle, where unit tests are fast, they're isolated, they're repeatable, self-verifying, timely. The thing about unit tests, though, is they're sometimes seen as this scaffolding that you build, and then it's no longer useful after you've already built your code. That's not true. That's not true in the slightest. It's not throwaway work. We'll get into some of these early unit tests in a bit. These are not a replacement for QA engineers, not a replacement for integrations. That stuff is all very useful still. It's another method of development and testing to ensure that the code you're writing from the ground up, from the moment you start writing any piece of code, does what it's supposed to do. So how do we unit test at Dolby? Well, we use different frameworks, but I use Google Test. That's my recommended. There's other ones like Catch, and of course, JUCE unit test exists as well. But the question remains, and I'm sure you're all here for this reason, how can it apply to audio? And how is this any different from cancellation tests? What can it do differently than just throwing content at things will do? Again, this is the first principles unit test. Open up any test-driven development book. They'll talk about this stuff. But it's designed to change your development style and really keep you in the zone, keep that iteration cycle fast. But as part of the first principle, I'll add maintainable. A lot of the code that we work on as test code, I've seen becomes very brittle itself. It becomes hard to understand. The reasons for each test start becoming this legacy code where only one person understands it. I have certainly written a lot of unit test code that I look back on it, 3 months from now, and I have no idea what's going on. We'll talk about how to try to prevent that from happening. So unit tests very much related to test-driven development. What is test-driven development? If you're familiar with this, you might know that it starts out with you write a failing test. This is the first piece of how you develop in this test-driven style. It can be very simple. It can be just that 1 equals 1. Now, 1 equals 1, if you just write a test for that, it will probably fail, not because 1 doesn't equal 1, but because you don't have your build system up and you don't have your project set up. That's a perfectly valid failure. Whatever that test is that fails, you make it pass. Do whatever you need to do. Some people say do the most smallest increment of code that you can possibly do to make it pass. That's great for a kind of a development style to kind of start learning this process, but eventually you'll start being able to code in larger blocks. Once the test that you have passes, you can refactor it. You, by definition, has a system that passes all your tests. It does exactly what you've intended it to do. And so any refactorings you make, by definition, as long as the tests still pass, the system will still work. Now, of course, that's ideal. We know that's not actually the case unless you have 100% pure test coverage. But I think the most important thing about test-driven development, this is not about testing. This is not test development. Tests are simply a byproduct. The word test-driven, that's, there's a hyphen there for a reason. It's a development style. It allows you to focus on a user's, caller's perspective. You're essentially establishing your API via a contract. Your API grows out of these tests that you create. And there's another concept beyond test-driven development called behavior-driven development. And this can kind of bring in more people from your team to this concept. And so rather than saying, when I input 1 into the system, it will generate this response, behavior-driven development, and I'm not going to talk too much about that, but I encourage you to look it up, is more about like, if I have a limiter, and we know this limiter should have certain specs because our product owner or our users say we want a limiter that is a peak limiter, it's not going to go above unity. In any situation, you can write that in plain text as a test and then code that logic within your tests. Again, it changes your development style. It changes how you're writing code and why you're writing code. So, it's a question I was talking with you about. We get a lot of pushback. I've certainly gotten a lot of pushback when talking about test-driven development in audio especially, because audio is different. Test-driven development came from the web world, where, at least from our perspective, everything is very much if this then that, if this then that. It's structured. But audio, well, my code depends on these outside libraries, which I can't test. Sure. We're going to talk briefly about the concept of mocks, though. And mocks can be used with audio as well. You can say, there's this really complicated algorithm that I didn't write, or maybe I did write it, but it's legacy code. I know it works. We're not going to test that yet, but I'm really interested in the interactions with that code. So we can mock it out. We can say, regardless of what this responds, how this responds to an input, just make sure that the glue, the interfacing, works. One of those cues I hear is unit tests can't hear that an algorithm is correct, just like our ears can. Well, can you really hear audio problems? I mean, a delay, it might be off. You might hear clicks in the audio, but I certainly have many times gone into algorithms where they're made up with these large graphs of DSP. Turns out one of the underlying DSP algorithms completely did not work. But because it was either a filter inside of a deep, complicated algorithm, we couldn't hear it in the final product. It was only during some coded investigation we realized, wow, it never had worked in the entire development. Another excuse, well, precision differences between compilers, platforms, fixed float, make it impossible to unit test, because the differences will, of course, get into our system. Possible? No. Difficult, of course. So most unit testing frameworks come with this near or float expectation. So you can say, these results should be roughly equivalent to the ideal, rather than bit exact. I said this before, but audio isn't like web development. I think we're just being stubborn then, because audio DSP is math. Math is testable. Math is physics. We can show that certain properties are true. Even this subjectively designed code, that we have this amazing algorithm that sounds great even though it's not an ideal filter, an ideal dynamics processor, that's testable. We need to code our design decisions as tests. So why did you choose a certain filter a certain way? Why did you choose to put saturation in your delay line? Some other excuses, oh, it's good for simple things, impossible for complex things. I would agree, except replace impossible with difficult. This is not going to revolutionize your development style overnight. It's a practice like anything else. Unit tests take time away from DSP development. True, but fixing buggy code in your release cycle also takes time away from DSP development. And I would agree, unit tests don't ensure bug-free code. Nothing does, but it's another tool that we have at our disposal. So a lot of the problems that I've found is not necessarily in DSP code itself, but the code surrounding DSP, the glue, the plugin, the hosting code. Mentioned before, we can mock DSP blocks, which I'll show in the next slide. What do we mean by mocks in the audio context? Have a complicated filter. If we want to test that that filter is hooked up, we don't need to rely on the exact response of the filter. We're going to mock them, maybe as a pass-through, maybe just whatever you get, just output it. We don't care about the audio in this situation. All we need to know is that something going in will be going out. Maybe it's mocked as a dummy response. We don't even care that anything's input. We just say, we're going to get some response that we can code in a unit test from a certain block, and based on that response, we'll do other things with it. We can check our inputs, make sure that we're in fact calling this correctly, regardless of what it actually does. Again, we're testing desired features, or the fact that things are hooked up correctly, not bit exact responses. We're at a JUCE conference. Let's talk about how JUCE can help us. These concepts are not specific to JUCE, but I was very impressed by how easy it was to basically create a plugin host with kind of the concepts that JUCE provides without ever having to launch a plugin host. So rather than launching Pro Tools, launching Ableton, and testing your plugin, you can, in code, create kind of a miniature plugin host. I don't even want to call it that because it's more of a test fixture that has direct access to all your plugin features with faster than real-time callbacks. No longer do you have to wait for a minute to process a minute's worth of audio. You can do this in milliseconds and microseconds. So here is what I propose as the hello world of a JUCE unit test. And it's really simple. We're saying test that, and I love names in unit tests. Names in unit tests are one of the most important things, I think, about unit testing. Test that my plugin has the correct name. We know exactly what that's supposed to do. We don't have to read any of the code below, but let's do that. We're going to instantiate my plugin. In this case, my plugin is a subclass of the audio processor. We're going to expect that plugin.kickName is my Radical plugin. Why would you do this? This is code that, if you're creating a plugin, it's just going to work. Maybe your plugin's name will change. So why would you ever put this in a test? Well, I would counter that when you write this code, it will fail. That's the first condition of a unit test. Write a test that fails. In order to make this pass, you have to get your project set up. You have to inherit from audio processor. Well, not really. You could probably make a plugin that didn't inherit from audio processor, but in order to have git names, certainly that would help. And your project must build successfully and return the correct string. Those are some great things to have as like this getting started project. You don't write this because you get it wrong. You write it to lock in this behavior. Some more things. Once we start getting with more advanced tests, we're going to want to use test fixtures. We're getting to this kind of rudimentary plugin host perspective. Maybe we want to write tests for our parameter lists. Certainly, once we have a plugin working, we have a certain list of parameters. We don't want that parameter list to change because of backwards compatibility reasons. Because if two of them were to switch in our plugin host, suddenly our plugin would no longer be compatible. That's a perfect thing to write in a test. So, another example. Apologies for not formatting the names and types correctly here, but we just have a plugin fixture called my plugin instance, and all we're doing is we're just making an instance of our plugin, glue code, that every test now has access to an instance of plugin. And so we might write that my plugin instance has the right number of parameters. Param size equals 2. That way, if we ever want to add a parameter, this alerts us that, oh, we're changing behavior. So make sure you know what you're doing. We're going to test that our parameters have the right parameter IDs. We don't want to change them out from under our users. Again, we're establishing contracts with the code we're writing. Some other simple things. more of a behavior-driven development. Your product owner comes and says, well, we have to now support stereo, or we have to support mono to 5.1. Okay, well, we can just write that in our code, but what better way to do that than by first writing a test? This will fail at first. Then to make it pass, you have to actually support mono to 5.1. You're not going to get this code wrong necessarily. You're just locking in your behavior. Finally, we probably also want to test actual audio stuff. And this is where our test fixtures become more of an audio host. So we're going to do these things in green here. We're going to enable all buses. The only reason we have to do that for our plugins was we're doing a lot of aux output stuff on Pro Tools. Then we're going to set our rate and buffer size. In this case, we hard-coded 48K. But if you want to make more advanced test hosts for your unit tests, yeah, maybe you can have that parameterized. Then we're going to prepare to play. That's all we need to do in order to be able to call process. Now, in this case, I'm not doing anything because I don't know what my plugin necessarily will do. I don't know what I want to test. And this is OK. This test, even though it doesn't do much, is fine. Once we get to that process block, and that we can call it without crashing, we have a plugin that can handle audio. Yeah, it might not do anything correctly, but we can code that later in our tests. This is it. This is test-driven development. Now, it's the first stage of it, certainly, but we're writing failing tests. We're deciding on a result. We're coding our behavior in those tests, and hopefully making our code more stable in the process. We're thinking from a user's point of view. Let's go further. Let's test that our controls are hooked up. So if you've never seen mock injection, this is kind of how we're doing it. We are kind of abstracting away our underlying plugin. We're saying, I don't care what the actual audio does. All I want to know is that when I call set value with a value of 0.8, that I get something internal, this set gain property, that it's called one time. That's a test that doesn't rely on audio. It just says, well, my gain control is hooked up. Great. Now, if ever we change it and we break it somehow, that the gain is not hooked up, that test will fail. So what is mocking? Mockings are glorified stubs. If you've ever worked with stubs, they're just a way for you to ignore, abstract out features. But if you use things like Google Mock, you can get really advanced features like call counting, argument checking, return value injection, really powerful things. You might not use them, you might. But as a result, your tests will be faster. If you have an algorithm that takes, God forsake, you have an algorithm that takes slower than real time, you can mock it out and test the algorithm, or test without the algorithm. Maybe your development team is working on speeding up the algorithm, but you can write your tests and they'll run in milliseconds, even though you have this really slow thing. I recommend Google Mock. But what this ends up doing is that when you mock things out, suddenly this my plugin test output binary, it no longer depends on your actual internal algorithm library. It depends on a mocked version. And so that my plugin test kind of command line test runner runs really fast. And you can do that after every change. You can put it on your command line server as a CMake or however you call your build and test process. And a side note, and I think I'm going to get to this later, but doing test-driven development this way, as you see kind of in this structure, it makes your code more modular. Suddenly we have a library at the top that is my algorithm that is completely abstracted from any knowledge about being a plugin. You can embed it in embedded systems. You can make it a plugin by just wrapping it very simply with JUCE. And then you can output a test binary. You can output an AX, an APST, an unknown custom plugin format. Doesn't matter. So definitely modularity is an extra benefit of test-driven development in plugins. Being able to develop these internal libraries separately from our plugin, having a nice seam between the two. We are also separating this out from the front end. You know, we've all written plugin code where we have a lot of logic within our user interface. It's very easy to do that. But by developing in a test-driven style, suddenly that seam is kind of, we force ourselves into that seam where our test runner has no UI. We can no longer rely on, you know, any work that we do being in the graphics section of our code. It makes our code more modular and easier to use. It also is great at documentation for yourself and for other engineers. You give engineers example code, you give engineers unit test code, and you can see, follow step 1 through step 5, exactly how to use a certain feature. Let's go further. Let's go into DSP testing. How do we test an audio algorithm? We said cancellation tests are good. They're a bit naive, but good. They don't provide any insight into your algorithm. Once you've ensured that you produce a certain response based on an input, you don't know if that's right. You don't even know why that response is the way it is. You know, is it correct? Is it not? All we know is it just exists and has not changed since the last time we generated that output. What if a filter design changes? What if we want to add saturation to a delay line? Well, we have to regenerate those outputs. Every algorithm and DSP process has a different nature. One size is not going to fit all here. So for a filter, think about what's your cutoff frequency. Maybe if you're deciding on different passband ripple, this is stuff that can actually be encoded into a unit test. You can actually put an FFT algorithm to change everything into the frequency domain and say, I must exactly have no more than a certain amount of stop band. Or I must, you know, must be rippleless. I don't know. Whatever filter you're designing. For delay lines, you can actually test that, yes, you put a sample response, an impulse response in, and then 10 samples later it should be output, maybe with different characteristics. Dynamics, I've used a lot of step functions, maybe a step function with another impulse response. That way you can see, oh, you know, it gets to a certain level, and then maybe with the impulse response you see a curve drop down as it's trying to compensate for the peak. Or maybe you can see the attack and delay. Those are things that, through math, you can actually code into unit tests. Or other effects. It gets pretty complicated if you have larger blocks, maybe that are not so standardized. But sine waves, frequency response, white noise, all these things are important. And bonus questions if anybody knows what that fourth box is from. It's the most complicated algorithm ever made. Special topics. GUIs. I have heard the notion that you should not test GUIs. And in some ways, I would agree. But I would say, like I did before, all your functionality should completely be testable without UI. You should be able to control this via command line, and it should be able to, you should be able to do everything you want. Whether it's meters or controls, you can also test those components. I'll show in a second. One thing you might be able to do is render to a JUCE image. Now, maybe you probably don't want to do bit exact image response unless you're really concerned about that kind of thing. But you can do like text formatting, text conversion. That's separate from the image rendering. You want to make sure that you add the % sign at the end. You can test for that to make sure that below a certain value, you get the negative inf that you want. I would recommend not testing position, not testing look and feel. This stuff changes a lot. There are actually better ways to test this that I won't get into. That's more of a system level test, but it's doable. This is the worst piece of code that I'm presenting, especially because you can't barely see it. But what it's designed to do is like test that a dB meter lights the bottom and middle segment at 6 dB. Pretty descriptive, even though the meter might not be itself. Let's say that our orange section has a level at 6 dB, and this is just example code. It's probably horrible. We're going to put a value into the meter, and we're going to render that meter to a JUCE image. And we're just going to test that the bottom two segments are lit and the top segment is unlit. Now, horrible code, yes, but I still think it's valuable, maybe as a temporary measure. Another topic, performance. We all want to get our algorithms faster. We can establish some performance goals, whether it's an absolute goal or a relative goal. We can box in our current performance, make sure that whatever we do, we don't destroy our performance. We can write it as a unit test. One question that I still have is often performance is threading related. Maybe it's a UI interaction, maybe it's something else. Suggestions? I don't know. Maybe that's not unit testable. Maybe that's more of a system test. But put that in your heads. Here's a very rudimentary performance test. We have a piece of code, process block that we want to test. We're going to wrap it in a couple of newfangled C++, blah, 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 maybe 11, 14. I don't know where they came into. I just started getting into modern C++ about a year ago, so I'm still learning a lot. But this was great when I found this out. You can just create a diff and say, I'm going to push all these diffs of every time I run this algorithm onto a vector of times. And then we're going to say that our max performance time should be 24 milliseconds. I don't know what that value necessarily will be. And that the average should be about 20. So we're establishing two different performance metrics. I'm sure you can find fault in this because different machines will run at different speeds. Maybe we want to establish a baseline with some known performance code. I don't know. Multi-threaded. This is tough. I think it was mentioned a couple of other talks that we really want to limit the places where multi-threading is a concern. And that's definitely important. You don't want to have to test this in every single class that you have. Again, C++11 has some great threading primitives that make a code like this possible, where you're taking, let's say we're testing some sort of object metadata state. It might be a FIFO queue under the hood. And we just want to push and pop in separate threads. We're going to take it in one thread. We're going to say, let's just put a bunch of stuff on the queue as fast as possible for 100 milliseconds. And then our main thread, while that's running, we're going to pop a bunch of stuff. And we want to make sure, A, that that doesn't crash the machine, and B, we only have one metadata state at the end because of the nature or the idiosyncrasies of this code. Again, rudimentary. There's probably a lot of fault you can find for this. But it's a good starting point, and it runs in 100 milliseconds, which is really fast and is nice. Oh, and by the way, this code actually did find a bug in a multi-threaded implementation of a queue. Some more advanced integrations that are possible now. Command line plugin hosts. We're getting out of the realm of unit testing, but still in automated testing. Codebase. Codebase provides their command line VST host. Kind of a lesser known feature Pro Tools actually does too. It's called Dish. It's not very well documented. It's very powerful though. I used it internally when I was at Avid, and it was very difficult. It's even more difficult for me now that I don't have access to the information, but it is there. You can actually test your AX plugins in the command line that Pro Tools provides in their development kit. File system. If you interact with the file system, there's issues there. I'm not going to go into them because I haven't had to deal with that. Network, external hardware, all of these dependencies, maybe you want to mock them out. Maybe you need to do something more advanced. I don't know. So, in short, audio plugins can be effectively unit tested. I know there's a lot of open-ended questions here that I maybe posed, and some of you are coming out of this saying, he didn't show actual code to test filters and dynamics and stuff. But this stuff can be done, and I'd encourage you to kind of orient your thinking in a different way. Whether you're actually doing TDD or not, think about how you can test your code as you're writing it. I'd recommend using Google Test and JUCE to drive test-driven development and drive the behavior. You don't have to use JUCE. You can just use Google Test. You can use Catch. But again, establishing contracts and thinking about your code from that perspective has definitely changed my development cycle and style. And this further allows you and almost requires you to modularize your code. And I think will become better as a result. We've all had code that, although it works, maybe you want to use a certain section here and you just can't, because you need to include all these header files, you need to include a large library, maybe you'll get conflicts between new modules that you start to piece together. And in Dolby, certainly we have over 800 engineers among 5, 6 different geographies, and we're not talking to each other as much as we should be. A lot of you have the benefit of being a smaller company, maybe a company of one. But even still, if you want to ever partner with companies, maybe you want to have your algorithms licensable to other companies, this becomes imperative. You have to be able to modularize your libraries. And the more code under test, even if it's that basic stuff, even if it's just number of parameters, even if it's just making sure that your input goes to your output and isn't being hampered by some stupid coding error, the less code that can accidentally break when you're developing more. You become more sane in the process. You become more confident that you run something on your local machine, put it to the build server. It's going to work. You have the tests in place. I am a beginner in this test-driven development stuff. And there's lots of people within the broader software industry that have said things much better than I ever will. They have much more ideas. These are kind of my 3 favorite sources that I've had over the last couple of years. Embedded C, as I said, I came from that world. We had a lot of embedded C code that was just simply not tested. And so getting more of it under test, how that we can get that under test, that's always key. Michael Feather's great book series, including this book. And then modern C++ programming, as we all know, is a lot different than legacy C++. It provides us a lot more functionality to make this test code easier to write and shorter and faster. And with that, I will leave it. So thank you.
Great talk. Thank you very much.
Thank you.
Any question for Ryan? Yeah.
Hi. First, thanks for your talk. I have a question. So you have unit tests, and you were talking about continuous integration, and that's also actually something I love. And you were also talking about performance tests, and so it's also actually something I would want actually like to make automatic through continuous integration. And I was wondering actually if you had any thought of that, because running on VM usually the timing are very different to a point where it's really actually even hard actually to set up a maximum. And wanted to know if you had any strategy actually for that. I would be very interested to know, please.
Not really. Your performance testing was what your question about. Yeah. As you said, VMs make it more difficult and means that you can't rely on wall clock time. All I can suggest is establishing references to code you know should run either in equivalent time as to what algorithm you're developing, or I know there's ways to do it. I don't want to say Valgrind, but there's ways to put it in kind of a containing module that will actually time it not to wall clock time, but will substitute wall clock time for relative performance time. And I'm kind of getting hand wavy here because I haven't done it myself. Open-ended area, certainly.
Any other question? Okay.
Yeah, I'm just wondering if you have any experience with like unit stress testing. I don't know, imagine like a situation where your app, after hours and hours of operation, deadlocks.
Sure.
Any way to catch these kinds of things, or?
I mean, I think as a first pass, you're probably going to be finding those either manually or in your large-scale tests, like whether you're running Pro Tools for an hour or so and then it starts barfing. That, I think, putting that in your integration tests that do take a long time is a great first pass. And the only thing I can offer is that once you have a developer or a situation where you start to key in on exactly what's potentially going on and you're able to localize that, that's when you can start attacking it from a unit test perspective and say, okay, we know there's something related to this this queue here, or we know that something's related to the cache that's starting to build up. And then you can write a unit test that starts from that base. You can say, okay, given that the cache on the computer is fragmented or it's all in a bad situation, then we can run code. And the setup code won't be trivial. The setup code will require some systems knowledge. But that's kind of always been my take, is like trying to investigate the problem that some of our testers are seeing to the point at which I can say, I think I know where to start writing tests.
And then you build up the volume of tests in that part of the code, and you create your mocks.
Exactly. So yeah, nothing that can like, bam, we can do this test and suddenly large-scale tests will be no longer needed.
Okay, thank you.
Yeah.
When it comes to testing things like audio quality and these sort of human, I guess, machine listening type situations, do you have a preferred Python library that might be used by the MIR community, or do you have your own internal libraries for doing that kind of stuff?
That's an area I really want to get into, and I haven't gotten into much machine listening as a test method. So unfortunately, I can't give you any answers on that. But I hope to at some point, and we actually have some researchers, I think, looking into that at Dolby, but they're not me.
Another question?
This is a question if you know of any sort of standard tools, but one thing I found when testing DSP is often you'll want to test an array of output against a known array, and just having a simple failure, or it says these indices of this array have failed, is a little bit tricky. Whereas if you had a plot of it, or you had some kind of extra indication, would make it faster to debug. Do you know, are there any methods or tips that you can give around that?
Sure. By default, I think as you've noticed, comparing arrays will be very verbose, and you'll just get two lists, and you'll have to maybe look to see what's the matter. In Google Test, you can actually write custom outputs for whether it's your custom types or whether it's arrays that make it easier for the output to say, in sample 5 on block 3, there is a difference of so-and-so dB, and maybe it's under your threshold. And so we do have some custom functions in Google Test that will translate raw sample values to actual dB comparison values. In terms of generating plots, I think we did that in a project a couple of years ago where any difference would be actually, I think the only place we got to that was they would take the expected response and the actual response, would subtract them together, and would just save a WAV file of the difference, along with the expected and the actual. And then the rest of the effort was left to the tester to kind of listen to it and provide feedback on maybe where it's going wrong. But certainly, in any unit test, you can, on failure, generate an image of maybe it's the frequency domain, image of any of the music features that you've extracted. I don't know. The possibilities are definitely out there, and they're possible.
Thanks.
Yeah.
One more question.
Cool.
Okay, so thank you again.
Thank you.